Very lucky we got over 20 talks in our session, and we go on in the morning as well. So I had to come up with little groupings. So this grouping here I felt was, more closest to the sort of the human emotion aspect, the human aspect of mathematics. I mean, obviously, they're all different facets of compassion. The reason, and if you remember from the description of the session, the reason I call this session Compassion as a Mathematical Practice is because I wanted to create space where we can acknowledge the passions, the human passions that drive mathematics. And so I choose specifically trust as one of those human passions, and I think hopefully see where we go, but we have some really nice talks afterwards as well. So I liked this title. My collaborators know I have a kind of a passion for language. Let's put it that way. So trust in mathematics. There are three readings that I intend with that. At least three. Maybe you have your own. There's a call for people at large to trust mathematics. Right? Just trust mathematics. Then there's a call that's much more to practitioners, to people who engage with mathematics, to say that sometimes we should trust what mathematics is telling us. And then there's the more research-oriented, if you will, reading that asks, well, where does trust live in mathematics? Where is trust in mathematics? So I intend all of these, and I'll go through these. So when you read this as a call to people at large, it is a bit analogous to trust in science that people often say, we often say. And, the reasons often are given as because it's objective, rational, absolute, universal, in that sense that we're after some truth that's uncontestable. It allows us to eschew the vicissitudes of the human condition, the specificities, the messiness of the real world, right? Which entail exceptionality. We're all different and exceptional and particular, specific. We're all subjective, right? We all see the world from a subjective perspective. So, in some ways, the appeal of mathematics, or science for that matter, often is couched in these terms. And the passions are seen as irrational. We instead, this is a little bit of royal we, I don't mean to speak for my collaborators, but we meet often enough to kind of feel sufficiently comfortable to use the we anyway. We take the perspective that passions motivate us for anything that we do, including the mathematics that humans have done for millennia. The choices that we make for what we end up studying, for the questions we ask, and the types of answers we accept. Like any other human activity, it is motivated by our passions. So I want to foreground the passions. I see the word compassion is with passion, right? So mathematics with passion, but not avoiding the passions. Rationality, on the other hand, the attribute of rationality that was supposedly one of the reasons why we should trust in mathematics, is very contextual, right? What counts as a rational action, a rational choice in one context, might not in another context. After all, rationality is interactive. It depends on what you see others do. It is a property of the stories that we tell to make sense of the world. Certain things make sense. It's rational because it makes sense relative to the other things you took for granted, to the sequence of storytelling narratives that you use to make sense, including in math, including in meta-mathematics, why we choose this set of axioms or another. So often people who hear a call at large to trust mathematics or trust science, they see it as an oracle. They'll give you the answer, trust it. In the late morning group, we had a discussion about AI, which felt a little bit like that. Maybe AI can get to do mathematics, and then we're supposed to just trust that it does it, right? Maybe that's what math is. If it's right, it's right. Never mind whether the book tells you. I mean, I know Ben would disagree with this, and rightly so. But let me play devil's advocate. This is how often people at large hear an appeal to trust mathematics. Our students as well. But it doesn't engender trust. It almost like usurps it, or at least states that it deserves it. And it can make people feel powerless, threatened by the power of mathematics, disengaged for sure. I was saying again to the group in the morning that as mathematicians we have this unique privilege that we have access to essentially the entire human population for the formative years of their lives. And the vast majority of them are left feeling like math is not for them, but it's actually against them. Not only they don't feel they belong in math, but more and more they feel threatened by the power that is wielded by math. So, something has to change. Okay, now, transitioning to the call for the practitioners, right? This is the call that a mathematician feels to trust the math. Like, trust what the math is telling, that math is something other than what I'm saying, that you're communing with something bigger than yourself. Trust in the creative power of mathematics, right? That it engenders new truths, it brings forth, it entails new things that you didn't foresee, you didn't put in by hand, we say. Plenty of examples, all working mathematicians have this experience. That it can hold multiple perspectives, multiple ways of seeing why something is true. This is very central to the mathematical experience, but unfortunately it doesn't often make it into the classrooms, into the experiences we share and curate for, again, the vast majority of the people who we have under, in our classes. So, sense-making, I claim, sense-making, I claim, relies on positing something new that is exceptional at the time you posit it, in the sense that it breaks some previous rule, something we previously expected. Because if it was playing along with what we were expecting, we wouldn't even notice it. It's just the expected thing. We wouldn't even have to call it out. So we call it out because it's something new, because it's something that didn't quite match. And then we posit it as possibly being true. It breaks a rule, but it doesn't undermine the rule. It just lifts us to a higher level where we see the rule as part of a process. Think of the existence of the square root of -1, for example. Right? There are many examples of this kind. We'll see some examples, in fact. So let me, I want to share, if this works well, a couple of videos from my classrooms. So let's see if the audio works. Oops.
Okay. The points I have in the circle will be exactly like this. And then I'll just have the zero.
Because it's tricky.
Yeah, so I would say, meanwhile, if the origin is
Then my vector will look like this. And then I'll have to back out like this. And I'll pick a second.
you still get a circle, right? You still get a circle with the same distance. Yeah.
Wait, is it the same distance?
I forgot the other one. Is it the same radius?
It's just a linear transformation.
Is it the same?
I don't know. I know what it is. I think
If you want to learn what theorem is, yeah.
I don't understand. I don't. Yeah,
So the results and stuff are the same.
So, right, if we have a circle, right? Let's just say even our circle is a big origin right here.
Yeah.
And let's just add a new point here. Let's not even bother adding a new origin. Because we add a point, and if we add, let's say, this point here, it is going to be just translated to the circle up here, right?
Oh, that makes sense. Oh, that makes sense.
One down, one down. Okay. You good with that, Jason? How all unit circles are we doing the same shape, so their location doesn't matter. Okay. E equals and because if we add a point to a shape, it just gives you the original shape. points are like the identity of space. They're the zero. Yay!
I think this is that the origin point? Because that's what we just demonstrated here.
Any point.
This has
Oh, right, yeah. Any point, it's gonna just like translate.
So we like things that are identities.
Infinite will.
Well, but they're all
one. It's all a point. It's all points are the same. What point is?
Okay, that was one. This was from a class in convex geometry.
The first realization I had was when I started the problem, it didn't make sense, and I went through some examples and thought I had found a counterexample, and that was like, I didn't realize that once you start subtracting numbers, you have to change the expression of the last thing. You can't just write like -1, -2, etc. And it made me question, like, when writing the problem, how can we tell like what the author omitted on purpose versus on accident, and like, is there like there's just so many questions around that. And then the other thing was like, it just kind of made me realize that when you're wrong about something, it's easier to assume that the way the problem's written or just the nature of the problem is wrong, as opposed to that you're wrong. And so when I first encountered the problem, like, I go to Ted and I said, I think I'm wrong, but this seems like a counterexample, right? And so I guess the realization there is like, we're so biased to just believe that we're right all the time.
Okay, that was from a course in math and philosophy last spring, and they were talking about the Goodstein sequence, for those of you that know, that were studying properties of the Goodstein sequence. And finally, final little one.
So, first of all, we can think of linear constant coefficient differential equations as polynomials in this differential operator d by dx. So in this example here, y double prime minus 3y prime plus 6 equals 0, we can kind of factor out the d by dx and create a polynomial, d by dx squared minus 3 times d by dx plus 6, and multiply that polynomial by y to get the same differential equation.
You see below, basically what this is doing is transforming the secondary operator operating on d by dt into a function or a map from function space to function space, rather than a map from real space to real space. So in all of these instances, e to the exponential function here, for instance, isn't strictly speaking operating on a number, it's operating on an operator that modifies the operator so that it is no longer the operator d by dt, but rather the operator, the exponential of d by dt. Specifically, we're looking at e to the d for reasons that will become very clear. Here, d is just convenient shorthand for the d by dt operator. And by definition of e to the d, the power series definition of e to the x produces this result. You can manually verify that this is equivalent for the e to the x and e to the d here. The argument is entirely routine and basically identical to the argument for e to the x, and that it follows strictly from the definition of e. But essentially what we get is this suspiciously Taylor series-like expression of the sum of all 1 over k factorial d to the k, meaning the kth order derivative of whatever is placed after this. This is not actually a function or an equation. This is an operator equation, demonstrating that the operator e to the d is equivalent to this set of operators on the right-hand side added together.
So one thing we were looking at is what happens when you multiply or apply the operator e to the cd to a function f. And basically what we did here is we used this definition back in slide 4 that Pascal talked about, basically expanding e to the d or e to the cd using the Taylor series definition, and then rearranging the elements. For example, d to the k f of x goes into the numerator of that fraction, and we rewrite the constant term to better satisfy the definition of a regular Taylor series. So the second line here, with d to the k fx over k factorial times x plus c minus x to the k, the sum of that, I forgot to write infinity, but the sum of that is a regular Taylor series, which actually just evaluates to f of x plus c. So when we apply the operator e to the d c times on the left, we're basically shifting our function by c. So this is just a horizontal transformation of an arbitrary smooth function f where all the derivatives are bounded.
So some of the further questions that were inspired by thinking about this prompt is just how far we can take this idea. So one example of this is d to the ed, where the front d isn't actually applying the standard d by dx in terms of just adding a second order to the derivative. Rather, it's looking at how rapidly the derivative function changes when a different f of x is placed on the other side of it. Because basically, what gave us this idea is if you can treat operators just like any other function, why can't we take the derivative of, just like any other object to be operated on, why can't we take the derivative of that? Unfortunately, our initial explorations of this were foiled because it's surprisingly hard to define the limit as a function goes to 0. So rather than the limit of an integer h going to 0, you have to define how the limit of h of x, or an arbitrary function going to 0, goes, which is fairly obviously extremely path dependent and doesn't have a super rigorous definition. So we're still working on making sense of that one.
We were taking this maybe 10 steps further, and we considered if we can write any differential equation as basically using this d times e to the d concept, if we can write any differential equation in that form by basically extracting the differential operator to the side of y, which is our target function, and setting that equal to an arbitrary function, g of x. So maybe this sum, I'm not even sure if this is well defined, but maybe this sum could be used as a differential operator. We could consider that.
Thank you for listening, by the way. I know this was maybe hard to hear as well. But so this last bit was from a differential equations class from a couple of years ago, 3 years ago maybe. Hold on, let's. Oops. No, that. Just try this. Oh. Okay, this was a video that the students created for their peers. This is what they do every, a couple of months, every month or two. They create little videos to teach something to their peers, something that they learned. And so these two students were exploring a prompt that led them to polynomials of differential operators. Well, you can take what you will from these videos. Obviously, they're more than, if I could tell you what to get, then I wouldn't have given you the videos. But they're examples, I intend them as examples of trust in the practice of mathematics at whatever level of mathematics you're encountering. So that mathematics will tell you something that you didn't know, and you should be open to that. Another example of this, a more formal example, is the work that my friend and colleague David Spivak at Topos Institute has been doing for the last couple of years in his notion of plausible fictions. These are all links, by the way, the whole presentation, there's a QR code, and you can get the links at your leisure. There's a blog post that he has about it, and he talks specifically about, this quote: the only thing it takes to enact plausible fictions is to recursively and plausibly fill the gaps. So it's this notion of, we have some things we're certain about and some transitions between those things that we're uncertain about. And you have to just, before you fill it in, you have to believe that it's possible to fill it in. And he has this notion of how to create plausible fictions that fill them in. And he quotes Barry Mazur from now not that recent, but anyway, 2009, a roundtable that he participated in. Again, this is a link to the video, where he says, imagination needs something in order to apply itself directly to the largest realm it can possibly apply itself. And for that, it needs conveyances, like bridges. And perhaps mathematics is that, from my point of view. It's a way of conveying the imagination to its broadest reach. So there's an element of trust there. And now moving on to the last part of the presentation about where is it in mathematics? How have people tried to kind of portray it? In what way? I always like to share this little excerpt or excerpts from this talk that Yuri Manin gave to the Congress, International Congress, back in the 90s. Mathematics as metaphor. It has become, I met mine when I was a graduate student, so you can imagine he had a formative influence on me, and so I certainly use metaphors a lot in my teaching and practice of mathematics, but specifically I want to point this out, when he says one cannot tell precisely what mathematics teaches us, in much the same way as one cannot tell what exactly we're taught by a novel like War and Peace. The teaching itself is part of the process. So again, you have to trust that it's about something more than what you think it is, but more than what you're saying. But then I learned that Poincaré had made some statement to that effect way back, more than 100 years ago, when he likened mathematics, or he described mathematics as the art of giving the same name to different things. So again, there's an element of trust there. What is common? You're trusting that there's something that links them together, some similarity between these things that superficially look very disparate, right? Mathematics, this idea is very close to the heart of mathematics. We do it all the time. Bill Byers, in his book, some of you may know this book, How Mathematicians Think, he was quoting Wiles from around the time when he proved Fermat's last theorem. And specifically, I want to highlight this point, that it's like a creative light that I maintain, says Wiles, often emerges out of ambiguity. So mathematics is not about certainty, it's about the search for certainty. In fact, the doomed, in some sense, search for certainty. We know that we cannot get the perfect certainty we want. We're still driven by it, we don't give it up. But we have to thrive in the ambiguity that is where the whole sort of imagination, the new ideas come from. This is something that actually, so when I was teaching the class on math and philosophy last year, one of the earliest readings that I gave them was gave my students were excerpts from Adamar's 1940s book on the psychology of invention in the mathematical field. And so in there is an appendix, those of you that might know this. I mean, I grew up reading this stuff. I never imagined I would teach it, But where he quotes a letter that Einstein, so Adamar had written letters to many mathematicians, physicists, and so on, scientists of his era, inquiring about their discovery practices. And Einstein was one of them. And he wrote a letter to Adamar, and he printed that letter as part of appendix, I think appendix 2 of the book. And in that, Einstein says, the desire to arrive finally at logically connected concepts is the emotional basis of this rather vague play. Before there's any connection with logical construction in words or other kinds of signs. So again, a trust in your imagination, in insight that you get in the space of meanings, right? That you know there's something there before you even have words to describe them. Russell famously described math as an art, true spirit of delight, the exaltation, the sense of being more than man, which is the touchstone of the highest excellence, is to be found in mathematics, he says, as surely as in poetry. Now, this is a quote from his essay, Study of Mathematics, but it's also the epigram of Eugene Wigner's very famous 1960 article on the unreasonable effectiveness of mathematics, which I also teach now to my students. And in it, Wigner goes on to say that, he describes philosophy as the misuse of terminology. Apologies to any philosophers among you. I have every respect for philosophers, but as a misuse of terminology was invented just for that purpose. And then he goes on to say, I would say that mathematics is the science of skillful operations with concepts and rules invented just for this purpose. The principal emphasis is on the invention of concepts. What this tells me is that it isn't what we say that is what we mean. What we say in some ways is always going to be a little bit wrong, right? But it's the ability to conjure in the hearer something analogous to what we mean, so we can be talking about it before we have concrete words to describe them. This is very much part of the mathematical experience of trust. And again, I'm saying all these things because I want our students to experience those things. Ed Nelson, maybe I needn't introduce very much about Ed Nelson, but he was a mathematician, a very well-known mathematician at Princeton. he wrote later in life 2 essays that I'm going to quote here. One was this one, Confessions of an Apostate Mathematician. And he says, how can I continue, he starts this way, how can I continue to be a mathematician when I have lost my faith in the semantics of mathematics? And I didn't underline the last sentence here. It says, mathematics is the last of the arts to become non-representational. And then in another late essay called Mathematics and Faith, he says, meaning is found in the beauty and depth of these patterns, in unsuspected relationships between structures that previously seemed unrelated, above all in the awe of confronting the potential infinity that is the world of mathematics. So once again, it's not about what we say, right? But this, we are accessing, we are communing with mathematics that is out there, that we're seeing aspects of, but we never can define what it is, right? It can surprise us, it will surprise us. And he ends by talking about his friend Ernesto Bonaiuti, who's a historian, an Italian historian, former priest, a historian and philosopher of religion, who, this is in the 40s, right? So many of you don't know, but Ed Nelson grew up in Rome, and so this person, Bonaiuti, was old at that time. He said, for St. Paul, abstract truth, absolute laws, do not exist, because all of our thinking is subordinated to the construction of this holy temple of the Spirit, whose manifestations are not abstract ideas, but fruits of goodness, of peace, of charity, and forgiveness. Eugenia Chang, who's a collaborator, as a practitioner of applied category theory, has written this paper back in 2004 called Mathematics Morally, that I quote to my students often. She tries to refine the notion of why do mathematicians say morally this should be true, this should be right, right? What is the difference between something that should be right versus something we know is right? So she says that the main point is the question of why. Why is such and such true? Because we've proved it is no answer at all. Here's an example. Why is it possible for an irrational to the power of an irrational to be rational? Some of you may have seen this. Right? It says consider square root of 2 raised to the square root of 2. If it is rational, we're done. If it is not rational, then take that to the power of square root of 2. That manifestly is rational. Right? Think about what that says. This proof is beautifully unsatisfying. We never actually find out which of the two is the answer that we want. We just know that one of them must be. And it certainly doesn't tell us why. So she has this formalism of believed truth, proved truth, and moral truth. And so the understand, somebody, well, Ben, and earlier as well, but Ben certainly talked about understanding. Sometimes we forget why things are true. And she goes on to say that proof isn't about what is true or what we believe, but it's because it's transferable. That's its utility. It's not that it's convincing. Many proofs aren't necessarily convincing, but it's easy to transfer. I will end with in fact, this is the last slide. I'm not even skipping. Some questions that were actually inspired by, Francis, by your book. These are my versions of a selection of some of the questions you end the book with. And again, I've had the pleasure of teaching from that book. Whom would we read differently? This is probably my favorite question. And my favorite appeal to Simone Weil. How can we train ourselves to expect enchantment in mathematics? What is the art of engaging the meaning of patterns, which is supposed to be mathematics? What is that art? Why does math instantiate freedom when most math students don't see it? How can mathematical thinking improve the world? Thank you.